Thank you. Thank you for the introduction, and thank you very much for the invitation to speak here. It's really a great honor for me to be speaking for this conference in honor of Arthur. So one of my favorite theorems from when I was a graduate student is the theorem in Chapter 8 of Berthelot-Ogus. And what I want to explain today is some joint work with Matthew Morrow and Peter Schulze, which sort of really uses the construction in Chapter 8 of Berthelot-Ogus in a crucial way. So I'll mention what the theorem was when we get there. Okay, so I guess it's a joint with Matthew Morrow and Peter Schulze. And the setup, so I want to talk about certain integral cohomology theories and relations between them. So the setup I'll fix once and for all is the following. So C is going to be some complete an algebraically closed extension of QP. And so, for example, C equals CP. OC is the ring of integers. And little k is the residue field of OC. So this is a valuation ring, and it's a perfect field. And then we also have the ring of Wood vectors. Okay. And then finally, the sort of main object is going to be a proper smooth scheme over OC. So actually, everything I'm going to say already works in the context of formal schemes. So if you like, you can work in that context, but it's interesting enough in the case of smooth projective schemes over OC. So things with good reduction. Okay, so in this setup, there are certain cohomology theories that we know about. Eventually, but nothing I'm going to say. I think, yeah, I want to.
The paper on the archive, you assume, I think, projective smooth rather than proper smooth.
No, we assume proper smooth.
Thank you.
Right?
I think so.
I thought it was a proper smooth formal scheme. Okay, so since everyone already knows the paper, maybe I shouldn't talk about it. But classical P-Adic cohomology theories associated to this picture. So there's three of them that I want to focus on. So the first one is étale cohomology. And so by this I mean the étale cohomology of the generic fiber, which we'll denote by x sub c. And the coefficients are in ZP. And so this lives in the world of finite ZP modules. And so in the algebraic case, the fact that it's finite is classical. In the formal scheme case, it's more recent. And then if there's a Galois action, all the constructions are going to be Galois covariant. So if there is a Galois action, then we'll get a Galois covariant statement. So this is a theory coming from the generic fiber. There's a theory coming from the special fiber, which is crystalline cohomology, which we heard about in the previous talk. So this is the crystalline cohomology of the special fiber relative to W. And then the Frobenius on X on the special fiber induces an endomorphism of this. So this lives in the world of, let's say, finite phi modules over W. So it's a finite modulo of the ring of Witt vectors, and it has this endomorphism given by Frobenius, which will be called phi. And then the third one is sort of, so I have the generic fiber, I have the special fiber, and then I'm going to use the integral model. So here's de Rham cohomology. So this is the de Rham cohomology of this morphism. And so this is again a finite dimensional, it's a finite OC module, and it has a filtration coming from the Hodge filtration. So it's a finite filtered OC module. So these are the three theories I want to focus on, and then we know that there are sort of various comparison isomorphisms relating different subsets of them. And I'm not going to spell them out right now. like for example, Fontaine's de Rham conjecture tells you that A and C are essentially the same information after you extend scalars to B de Rham. And A and B is the crystalline conjecture, and then B and C is the Berthelot-August theorem relating crystalline with de Rham. Okay, so the goal for what I want to do today is I want to sort of try and explain a single picture or a single cohomology theory of which all three of these are specializations. So realize all three are specializations of the same, of a single theory. And already it's clear if you want to do this, you need something. So in each of the previous cases, the ring that I was working over was either ZP or W or OC, so it was a dimension 1 ring, it's a valuation ring. And if you want something that's going to specialize over two different valuation rings, it needs to be at least two-dimensional. And this ring is sort of the main sort of playground in this talk. So it's Fontaine's ring A-nth. And sort of going to be the object over which everything lives. And let me sort of, let me tell you what it is. So the definition, it proceeds in two steps. So first we define what I guess nowadays we call OC flat. It's by definition, you take the ring of integers of C, reduce it mod P, and since now you have a ring of characteristic P, it makes sense to talk about its perfection in the sense of inverse limits. So this is the inverse limit over Frobenius of OC mod P. So it turns out by a non-trivial theorem that this is actually itself a really nice object. So it's a valuation ring now in characteristic P with an algebraically closed fraction field. So C flat is going to be its fraction field. Oh, OC, sorry. And so roughly what's happening is that when you sort of take your valuation ring and reduce mod P, you sort of lose a dimension. So this is a zero-dimensional ring, but it has tons and tons of nilpotents. So when you pass through the inverse limit along Frobenius, those nilpotents sort of build up to give you an extra dimension. And that's what OC flat is. And then the ring A-nth is a deformation of this to characteristic 0. So it's the ring of width vectors of OC flat. And this is a perfect ring of characteristic P. So taking the width vectors is a really nice thing to do. And I will call phi the Frobenius you get by thinking of it as the width vectors of a perfect ring. And so this is going to be the basic object we're going to be working with. And I want to explain how it's related to the three rings appearing on the first board up there. So in order to do that, I'm going to choose coordinates. And this is not strictly necessary, but it just makes certain constructions easier. So I'm going to choose P underline in OC flat, which is a compatible sequence of P power roots of P. So you just choose a compatible sequence of P power roots of P in OC, and this gives you an element of this inverse limit, which I'll call P flat. And then by taking Teichmuller lifts, you also get the element bracket P flat living in A-nth. And then the basic slogan, which I'll try to make precise, is that A-nth is sort of, it's kind of like a two-dimensional regular local ring, and the two coordinates are P and P flat, P underline. So, and I warn you right now that what I'm about to write is completely nonsense, but that's why it's a slogan. So it's a two-dimensional regular local ring, and the parameters are P and P flat. P bracket P. And there are theorems that say that it behaves like such a ring, but for example, it's not two-dimensional, it's not regular because it's not Noetherian, and those two are certainly not parameters in any reasonable sense. But anyways, that's the philosophy. And the reason this is related to the previous slide is that because of the choice of coordinates, you can define these three explicit sort of rank 1 quotients. So you get 3 divisors on A-inf. So the first one is where you kill P. So if I take width vectors of a perfect ring and then I kill P, I just go back to the ring I had earlier. So I have OC flat. The second one is where you kill P flat, so the other parameter. And sorry, I keep saying P flat, but what I mean bracket P. Bracket P underline. So, I mean, this is not literally what you kill to get here. Here you use the fact that the width vector construction is functorial, and there's a map from OC flat to its residue field, which is K, and so passing to the width vectors, you get such a quotient. It is the case that this element is in the kernel, but for example, so are all of its P power roots. So this element does not generate the kernel. And there's even worse things in there.
And this is independent of any choices, this one?
Yeah, so the map is completely independent of the choice. I'm just to write it down. Yeah, the map is what I said. It's the functoriality of the width vectors. And then there's a third map, which is Fontaine's map theta, which goes to OC. And here you kill the difference of the two coordinates. So sort of I'm killing the horizontal direction, the vertical direction, and then the diagonal direction. So you kill C, which is P minus P underline. And this literally is true in that this generates the kernel.
Again, it's independent of choices, if you do it right?
Yes. So the map is totally independent of choices. This is just one convenient choice of representatives for elements in the kernel.
Is there a functorial definition of this map?
You can define it, for example, using the cotangent complex formalism. A-inf is formally a tau of a ZP, and mod P there is such a map, and therefore it lives to characteristic 0. There are more explicit definitions. Okay, so I want to work with this ring, and so I want to actually draw a picture of what it looks like. And so this is a cartoon of spec A-inf. And so if you've seen the cartoons Scholze has been drawing at Berkeley a year ago, I warn you that this is different from the one he's drawing. I prefer this because it sort of illustrates one feature that's relevant to what I want to talk about here. So this is really a picture of spec A-inf, so I'm going to draw the generic point. So here's the generic point. Here's the close point. And here are the sort of these three quote-unquote height 1 points that I'm interested in. And I will label all the points with the corresponding residue fields, so or extensions of residue fields. So the residue field of the close point is K. This point corresponds to the fraction field of W, so W join 1 over P. This point, so it's the generic point of this quotient over here. The point in the middle is the generic point of OC, so C. And then the last one is C flat. And then there are specializations relating them. So I'm going to draw an arrow whenever there is a specialization. And oh yeah, I guess I didn't label the generic point. So it turns out that the generic point sits inside beta ROM. So I'll just label it by beta ROM. So that's a rough picture. I also want to go further. So I want to not only label the points, I also want to label the specializations. So for example, this specialization corresponds to the ring W, meaning this quotient A to W of K. This specialization corresponds to the ring OC flat, which is the first one over here. And the other one is the other one. So this is OC. Okay, and so in terms of this picture, what's going on? So let's see, let's write down, look at, maybe I want to label one more or two more. So this specialization, you can think of it as being W of C flat, meaning there's a functorial map from W of OC flat to W of C flat, and the quotient at the special point, the field at the special point is indeed C flat. So this is where W of C flat comes into the picture. And this specialization here, after completion, is what's called beta Rom plus. So this is a valuation ring, and its fraction field is beta Rom. And so the only thing missing is this guy, and this guy's kind of weird, so I don't want to name it. It's sort of closely related to the fact that the kernel of this map is not generated by just P flat. There's lots more junk in there. Okay, so in terms of this picture, what is going on? So crystalline cohomology is living over here on W. So it's crystalline cohomology. De Rham cohomology is living over OC. And Étienne cohomology, well, it turns out that there's a pretty nice way of thinking about it as living over here, which I'll explain once I write down the theorem. And maybe, okay. So these are where the existing three theories are living, and what I would like to explain is a picture of it sort of fills at this end. So we want to construct something that lives over all of A-nth, and it's going to have the correct specializations.
Is there any interest in it? It suggests it might be a theory over OC flat.
Yes, it's very interesting. So I'll comment about that theory once I write down what the result is. That's somehow like where the new information is coming in.
What about the mysterious error that you didn't want to name?
So the point is, if you label the specialization by the complete local ring at that point, then this guy just turns out to be W of 1 over P, because the kernel of this map satisfies the m equals m squared. So, and that's why it's kind of weird. Are there any other questions about the picture? Okay, so now I have to figure out how to erase. Okay, so here's the main result. I think this was section 2. Yeah. Well, I guess it was section 3 probably. I think it should have been 3. So this should be 4. I'm following my notes. So results. And so the main theorem is that what I said we are going to do, we can do. But let me sort of say it in a rather precise and maybe slightly long-winded way. So again, I remind you that our setup is x over OC is proper smooth. And to this data, we can associate, or functorially attach a complex, which I'll call R gamma sub A of x. And so this is a perfect complex of modules over the string A-nth. And it has an extra structure coming from Frobenius. So plus a map phi sub x from the complex to itself, which is Frobenius linear. Semi-linear. So A is A-nth, yeah, sorry. Yeah. Thanks. So it's phi semi-linear. So with respect to the phi on A-nth, and it's an isomorphism after you invert this element that I had called psi earlier. And maybe this is not so important for now, but it'll come back later when I make a remark about this. And an isomorphism after inverting this element psi, which I remind you was a generator of the kernel of theta. With the following realizations. So satisfying Okay, so in my notes I have the étale one first. So, that one. So the étale realization is the fact that this construction recovers étale cohomology. And the way it does is that you have to go to WC flat and then extract a ZP module out of it. And here's how it works. So there's a canonical isomorphism between this complex, scalar extended to WC flat. So restricted to that height 1 specialization over there. And étale cohomology, ZP coefficients also scalar extended to the same ring, which is compatible with Frobenius. So there's a Frobenius on the left-hand side coming from the fact that there's a Frobenius on each factor, and there's a Frobenius on the right-hand side from the stupid Frobenius on the right-hand side on WC flat. And what this means is that you can recover the étale cohomology itself as the phi invariance. So this is by a theorem of Katz, I guess. So if you're interested in the étale cohomology, not just a scalar extension, then you can recover it by the following formula. So you take this complex over A inf, you extend scalars to WC flat, and then you sort of do phi equals 1. And if you sort of invert P, then you really do phi equals 1 on cohomology. Otherwise, it's the derived version of that construction. Okay.
Isn't it, I think that phi minus 1 is surjective on. So when you go from ZP to WC flat, it's a flat extension, and Frobenius minus 1 is, I think.
Ah, so you're saying the derived construction is not necessary?
Well, for cohomologies, you should get this.
Yeah, that's, yes. I just wanted to be safe. Yeah. So Katz's theorem is that if you have any perfect ring of Kersig P, ZP local systems on spec of that ring are the same as modules over the width vectors of the ring which are isomorphic to themselves after pullback along Frobenius. And so I guess, yeah, that's a good point. So I want to point out that once you make the scalar extension, this element C becomes invertible. Because remember, in this picture, the zero locus of C is over here. So when you base change over here, there is no zero locus. So the Frobenius is actually an isomorphism on the nose, not just after inverting something. And so you get a unit root crystal on WC flat, and thus it corresponds to a local system. Okay, so the others are more direct. So the crystalline realization is exactly what you might expect. So you take R gamma A of x, and you scalar extend to W of k, and you get the crystalline complex. Again, as phi modules. And so, for example, what does this tell you? So we know that on the left-hand side, Frobenius is an isomorphism after inverting Xi. Now, if you stare at the picture, the zero locus of Xi is over here. So when I restrict over here, that just means it's an isomorphism after inverting away from the close point, which is the statement that Frobenius is an isogeny on crystalline cohomology. And then the de Rham one. So again, R gamma A of x, translate over A inf. And now there's a choice. So I think the way we wrote the announcement, there's no Frobenius twist, but I'm going to twist it. So I base change along phi first and then specialize to OC, and then I get R gamma de Rham of x over OC as filtered modules. And I will explain, or maybe not, how the filtration comes about later. And I guess I want to emphasize, maybe this is clear from the title, but that everything is integral and on the nose. So you get some statements about torsion from this. Okay, so corollary. So maybe I'll write two of them. So the first one is, if you can ask what the relation is between the dimension of a talc homology with mod p coefficients and the dimension of crystalline cohomology with mod p coefficients. So the crystalline cohomology of the special fiber relative to K, which is also just the dimension of the de Rham cohomology. Because de Rham is crystalline. And then what you get out of this is that there's an inequality this way, without any assumptions on ramification. Sorry, my shoelaces are coming undone. And then there's an integral lift of the statement. So this is a mod p statement, and you can ask what happens integrally. And integrally, what we can say is the following. So if the crystalline cohomology is torsion-free in degree I, so is a talc homology in the same degree.
If X is X6, the dimension is HI tau.
Ah, yeah, sorry, thanks. Otherwise, it would not be so interesting. Okay, so maybe I want to make one comment. So first of all, the inequality in one is strict. So there are examples where there's genuinely more crystalline cohomology than there is a talc homology. So you can't expect to do better. And this is more or less the only direction that is reasonable if you sort of have some deformation theoretic picture in mind. And indeed, that is the case. And likewise, there are examples where the crystalline cohomology has torsion, but the talc homology does not. In fact, we wrote one down in our paper. It's a threefold Inkersig 2. And so this is the only thing that could be reasonable. And maybe I'll sort of just explain the proof of one.
So before that, can I ask a question?
Yes.
The difference in torsion and crystalline cohomology and in the de Rham cohomology, there are Ekadal's example, which shows that when ramification is bigger than p-1, they need not be the same. Do you have any way of incorporating that? And
I guess the short answer is no. I don't know what the relation, like a precise bound for the discrepancy between the two. I've been asking people if it's reasonable to expect that the de Rham cohomology always has less than or equal to torsion than crystalline cohomology. But I don't know the answer to any of those questions.
But if the de Rham cohomology is torsion-free, it's not enough to know, there is no implication, other implication of it. So all the implication between such and such is torsion-free and something else is torsion-free is in what you wrote, or that is, you have examples showing that other implications of torsion-freeness are not true?
The only implication I have a counterexample to is the other one, the converse to this statement.
So the implication that if de Rham is torsion-free, then
I don't say anything about de Rham. Well, so sorry. I mean, I guess I don't say anything about de Rham.
because all of them are torsion-free is just a numerical thing, which is the same as crystalline.
Yeah, so, okay, it is true. I mean, I can't think on the fly, but I think it is true that if all the de Rham cohomology groups are torsion-free, then in fact, so are all the talc cohomology groups. That follows from the proof. I don't know about a single degree how that argument would work. And the reason I wanted to mention the proof of one is exactly this point that Arthur raised. So you consider what happens over the new specialization that you gain, namely the 1 over OC flat, and use semi-continuity. So semi-continuity for this base change. So the point is, this is a perfect complex over OC flat, and whenever you have a perfect complex over some ring, the dimension of the special fiber, the dimension HI of the special fiber is always an upper bound for the dimension of HI of the generic fiber, and that's exactly what one is saying.
But this ring isn't Noetherian, right?
OC flat is not Noetherian, but it's not so bad. It's a valuation ring of rank 1 valuation.
It's still okay to use this notion of...
Yeah. I mean, for example, you can do some approximation argument to reduce to the Noetherian case. Okay. Maybe I should use these boards. No. Okay. So I wanted to make some remarks about the theorem. So maybe the first remark I want to make is that in fact when the crystalline cohomology is torsion-free in the setting of 2, you can actually say something finer. So if HI Cris is torsion-free, then this HI of this complex over A inf is itself a finite free module. So what you have is a finite free module over A inf together with the self-map phi, which is an isomorphism after inverting C. And these gadgets have a name, so Farg called them Breuer-Kissen modules. And he proved a very interesting theorem about them. So the theorem Farg proved is that if you have a Breuer-Kissen module, then the crystalline specialization is determined by the other information. So in particular, what that implies in our setup is that if you're in the torsion-free case, then the crystalline cohomology of the special fiber is a functor of the generic fiber, which is not easy to see from the definition. Okay, and then maybe for the second remark, I need more space. So the second remark is more about how the proof goes. And the way the proof goes is that you construct the cohomology theory by first constructing an appropriate sheaf and taking its cohomology. So more precisely, we construct a complex which we're calling A omega x, which is a complex of sheaves on X of A inf modules together with the Frobenius such that this cohomology R gamma sub A of X is just hypercohomology of this complex.
You mean intersheaves or what,
Sorry?
what kind of sheaves?
Étal or pro-étal, I guess, since it's some limit thing. Yeah, so constant sheaves with coefficients in A inf. And this complex of sheaves actually has very interesting properties. So there are two specializations that are, at least I find interesting. So the first specialization is related to what happens in the de Rham specialization in the theorem. So if you base change along the map from A inf to OC, which is Frobenius twist of theta, so the same one that showed up in the theorem, then the complex you get is really the de Rham complex. So this is the de Rham complex of X over OC. In particular, it's a complex whose terms are given by differential forms, and the differential is not OX linear. It's just linear over the constants, which is OC. But you can do something else, which is you can specialize when you don't twist by phi. So if you do that, at least if I got my twist right, then you actually get a complex of quasi-coherent sheaves. So in fact, you get a perfect complex. So it's a quasi-coherent complex on X, whose ith cohomology group, or sheaf, is given by omega I.
So here you are working with a formal scheme or?
Formal scheme. Yes.
So the X is a special fiber?
Yes.
Yes.
So this is the de Rham complex of the formal scheme over OC, and differential forms for the formal scheme over OC. And so this is a quasi-coherent complex. The differentials are all linear. And so this is kind of this mixed characteristic version of the Cartier isomorphism. So in particular, if you specialize both to the residue field, then you get the Cartier isomorphism.
So you don't, it's not the wrong bit, which you usually think of.
Okay, so I want to point out that this is the complex that somehow is responsible for the Hodge-Tate filtration when you invert P. So there's a somehow close connection between the two, which goes through this gadget over here. Okay, and then finally the third remark I want to make about this is that there's one specialization, or specialization in quotes.
Complex totally decomposed in the sense of.
So I don't know if there's an analog of the Dulin-Aluzzi theorem in general, but what is true is that if you just look at the obstruction to splitting off H0 from H1 in the one truncation of the complex, that measures the obstruction to lifting the formal scheme to A2, A-inf marked C squared. So there's a square zero extension of OC relative to ZP given by this length 2 quotient of A-inf, and the obstruction to lifting across that extension is the extension class that's showing up here.
So how can you build, you can have, when you tensor with small k, then the first line is, there is an extra Frobenius, but how can you then have a quasi-coherent complex, and when you tensor further by some Frobenius, you get a de Rham complex, which is not all linear, so I don't know, there seems to be something strange here.
Well, it should realize the statement that the Frobenius push forward of the de Rham complex on the special fiber has cohomology groups given by omega I of x over.
And this is on the generic fiber, so he did not.
Well, this is integrally. Maybe we can discuss this after the talk. I get confused about Frobenius twist like all the time when I think about this, so it's quite possible I have something off by a sign. Right, and then the third specialization, which I wanted to mention, is the A-Chris specialization. So in this picture, there is yet another period ring that's floating around, which is sort of the dotted arrow, which maybe is not so visible, which is sort of a spec of A-Chris, which is what you get when you join divided powers of the kernel of C to A-inf P-adically complete. And there is a analogous statement over there. So R gamma A of x tensor over A. So again, there's a Frobenius twist, I believe, with A-Chris is the crystalline cohomology of x relative to A-Chris. So this is the cohomology theory that we already knew interpolated between the crystalline cohomology of the special fiber and the de Rham cohomology of the generic of the integral model. And the theorem is saying that there's some way to extend it across all of A.
So all this isomorphism or almost isomorphism?
Quasi-isomorphisms, no almost. Okay, so those are the results, and now I'd like to explain what goes into constructing this object.
So this is an algebra, I guess?
Which one? A omega x? It's an E infinity algebra. Yeah, it's not a DG algebra. So one of the main tools going into the construction is this gauge transformation business from Berthelot chapter 8. So L eta is what it's called. It's a killing torsion in the derived category. And so the basic goal is the following. So this section is going to be kind of abstract, unrelated to P-Adic things. So let's say A is a commutative ring. And F is an element of A, which is a non-zero divisor. A question you could ask, sort of a naive question, you could ask is if there is a way to take a complex of A modules and systematically kill all the F torsion in its cohomology. And this recipe should be somehow independent of the quasi-isomorphism class, so it should work at the derived level. So the goal is to kill F torsion in some complex HI of K, in HI of some complex K, functorially in K. And this is not really possible if you try to do it using just nice exact functors, but I will nevertheless explain why it is possible. So the key definition is the following. So I'm going to define a functor which does this job, and to define the functor, I'll first specify what it does to nice objects, and then you resolve everything by a nice thing. So the nice objects in this case are complexes of flat modules. Or really, you just need F torsion free. And then you do the following construction, which is denoted eta sub F. So this is an example of the filtration de Calais for the P-Adic filtration. And so you construct a new complex whose term in degree I is the set of all elements alpha in the original complex in degree I that are divisible by f to the I, such that the differential is divisible by f to the I plus 1. I mean, you need the second condition in order to get a complex. And so this defines for you a new complex eta sub f. And then the theorem is that this recipe passes to the derived category. So theorem, applying it to flat replacements, say. Gives a functor from d of a to d of a. Which I'll call L eta with respect to f.
Definition of Decali, there is it's not a phi a ki, there is a kn plus I or something like that.
Well, if you can define you can think of the input as a filtered complex given by the P-Adic filtration, and the output as a new filtered complex, and what I've written down is the zeroth step of the new filtered complex.
Do you leave some boundedness in the direct category? Or bounded about?
Not for this construction, no. But I mean, for all you're going to do, it's going to be bounded below. It's going to be bounded, and it's going to be really nice. But
when you write f to the ki, of course, I is. You can allow formally I to be.
You can allow it to be negative, which is why, as you said, you need at least f torsion free. Yeah. Yeah. So actually, let me do an example where I is negative. And so the remark I would like to make is that this functor is not exact. So it's a functor between triangulated categories, but it doesn't take short exact triangles to exact triangles. And here's sort of why. So let's do an easy example. Let's take A equals ZP and the element F to be P. And consider the complex K, which is just Z mod P, placed in degree 0. So this is, we have to choose a flat replacement, so this is quasi-isomorphic to this two-term complex, which is multiplication by P on ZP, where the right-hand side is in degree 0. And so when you apply L eta to it, L eta sub P of K, you're supposed to apply eta sub P to this replacement. But if you apply eta sub P to the replacement and you think about what the indices mean, it means that you're, in the first entry, you're allowing denominators of P. And in the second entry, you're not. So this looks like the complex, which is 1 over P ZP, mapping via the same differential to ZP. And this is 0, quasi-isomorphic to 0. Because it's an isomorphism. But if you do the exact same computation for Z mod P squared, it's not 0. So you end up getting Z mod P. Just because everything looks the same except this differential is a P squared. And so there's a Z mod P in degree 0 in its cohomology. And so this is why it's not exact. If it was an exact functor and it killed Z mod P, it would have to kill Z mod P squared. But it doesn't. And this is really crucial for what we are doing. I guess to go back to an earlier question, so you can prove that L eta is lax monoidal. And so in particular, it takes algebras to algebras. And that's why the answer to Martin's question from earlier is yes. Okay, so how do you use this? So here,
What term monoidal?
lax monoidal. So a functor is lax monoidal if f of A tensor f of B has a canonical map to f of A tensor B. It's enough to make algebras go to algebras. So the construction is going to depend on a choice, but I mean, the actual construction does, but the output doesn't. So I'm going to choose So I remind you again that X over OC is this proper smooth formal scheme, and the construction is local. So let me just say it's smooth formal scheme. In order to do the construction, we are going to take a nearby cycles functor applied to a certain sheaf and then modify it using this L eta construction. So I need to choose an element F to do the L eta, and for that I choose the following. So epsilon underline is a compatible sequence of p power roots of 1. So a trivialization of zp of 1, if you like. And like before, we can think of it as an element in OC flat. So earlier I had p underline, and now I have epsilon underline. And the key element here we're going to use is mu, which is epsilon minus 1, which is an element of A inf. And so maybe I just make one remark about this. So one thing you could do, so I guess I should pick my normalization. So I think the way I'm doing it, I want epsilon to start at a primitive p root of 1 rather than starting at 1. So what this means, I think, is that if you do phi of mu, well, it's a compatible sequence of elements here.
Yeah, but you have to be careful where you start. And the indexing is 0 or 1?
Okay, so what I want is that when you apply this map theta to it, you get 1 minus a primitive p root of 1 minus 1 for mu. So it's not in the kernel of theta. And it's the closest thing that can be there, but it's not. So if you did phi of mu divided by mu, this makes sense. And this is actually a generator of the kernel of theta. And this is the relation to the previous, to that picture. So this could play, this is equally good as this element xi I had earlier, which was p minus p underline. Okay, so I mean, if you're familiar with computations of nearby or vanishing cycles in the P-Adic Hodge theory approach, sort of due to faultings and then Peter, this element shows up quite prominently because you're essentially trying to do group invariance under some actions, and the way you compute group cohomology is by gamma minus 1 or gamma as a generator. So that's roughly where this object is coming from. And what we're going to do with it is the following. So step 1. And this, look, the construction is in 2 steps, and the first step is you get an almost correct thing, and then I'll correct it in the second step. So this is almost correct version. Yes, of A inf, A omega x. Okay, so we're going to use the nearby cycles map, so let me give it a name. So nu is the map that goes from, well, either the étal or the pro-étal side of the generic fiber to the étal side of the formal scheme, just given by the fact that you can pull back an étal. So, sorry, this is a map of the corresponding topoi. The pullback functor just says that an étal cover of a formal scheme gives you an étal cover of the generic fiber. And what we're going to do is we're going to set A omega x to be the following. So this is A omega x prime because it's almost correct. So one thing you can do is you can do R nu lower star. So you can push forward along this A inf, but really the sheafified version of A inf on the site. So the construction of A inf makes sense for any ring. It didn't have to be OC. You can always reduce any ring mod P. You can pass through the inverse limit perfection along Frobenius, and then you can do the width vectors. So you can perform that construction as a sheaf on the pro-étal side. And I'll call that sheaf A inf comma x, and then you push it forward. And okay, so that's complete nonsense if this is the first time you're seeing it. I'm sorry, but I wanted to give an actual definition. And then this guy is sort of not good, because for example, Frobenius is an isomorphism on A inf, so Frobenius is an isomorphism on this complex, and it certainly is not going to be an isomorphism on our A omega. So we're going to modify it using L eta. So do L eta sub mu of this. And the Frobenius now on this guy, which is an isomorphism, now induces a map which is not an isomorphism. It just induces an endomorphism. So this is an object of the derived category of the formal scheme of A-inf modules, and I can.
So here the etal, X etal is the special fiber of the formal scheme? Or?
Yes.
And the left is the rigid point?
Yes. Yeah. So we also get a map phi, which goes from phi upper star of this complex to itself. And if you sort of understand how L eta works, essentially when you do apply phi upper star with L eta, it basically commutes, except the commutation's off by an element here. Instead of doing L eta mu, you do L eta phi of mu. And so therefore, the canonical map is going to have a kernel and co-kernel, which are killed by phi of mu divided by mu, which showed up over there. So this is this map. So it's an isomorphism outside the kernel of theta. And that's just a completely formal calculation based on the fact that phi of mu divided by mu generates the kernel of theta.
So the point is that L eta doesn't quite compute with phi star. Can you say that again? You said something really fast.
I said if you do L eta sub little mu of phi upper star, that's the same as, no. Let's see. Hello. I think L eta sub, if you do it in this direction, then that's the same as doing L eta phi of mu, phi upper star. Just because phi is an isomorphism, so I'm just transport of structure. And so, yeah. So in fact, by the similar formal argument, you can actually prove the following. So we have this, we produce this map, phi upper star a omega x prime to a omega x prime. And on the other hand, you also have a canonical map here from L eta with respect to this kernel xi, which was phi of mu divided by mu, to a omega x prime, just because this was a subcomplex of things satisfying certain divisibility properties, and there's a canonical isomorphism like this. And so this tells you in a precise sense how far this map is from being an isomorphism, namely, is the highest power xi you need to make this map an isomorphism, and that's determined by the number of non-zero cohomology groups.
So this isomorphism is the one in capital August?
This isomorphism is just phi, I think.
To L eta?
Yeah, it's the way phi works with L eta, so there should be a Frobenius here. But it's completely formal based on how L eta works.
Yes, so it's in essentially.
Oh, sorry, you're saying it's in the book?
Yes.
Oh, okay. Excellent.
The main thing in capital August actually, the L eta and the phi.
Right.
So this is the key.
But I guess in their case, well, phi of p is p, so yes, thank you. Okay, I lost track of which board I was. Okay, right. So this is the almost correct construction, and this is almost correct in the sense that this is almost isomorphic to what we want. And to get something that's honestly isomorphic, we had to fix this almost nonsense. So I haven't actually done any almost mathematics, but what is really going on is that this is living in the almost. Well, you can think of it as living in the almost world, and you modify it by something supported on the special fiber to make it correct. Is it clear why you needed to kill the torsion?
What's the purpose of the L eta? Why did you put it in?
So if you try to compute nearby cycles in this framework of perfectile spaces, say, there's just a lot of bad torsion that shows up when you compute these nearby cycle sheaves. So for example, if you did it instead of A-inf just for the structure sheaf over here, the torsion would be sort of really like infinite. But the observation is simply that whatever that infinite torsion is actually killed by epsilon p minus 1. And so when you do this L eta, it just goes away. Okay, and then the second step is you fix the almost nonsense. So Step 2. So, I mean, the way you do sort of, you have something in the almost world and you want to get something in the real world, the way you do it is that you modify it by something that lives in the quotient of your ring by the ideal of almost mathematics. So in order to do that, we're going to do the following. So we're going to construct well, I'm just saying you can do this. So you construct a natural map which goes from the de Rham-Witt complex of the special fiber, thought of as a complex on the formal scheme, to this complex, A omega x prime, scalar extended to W. So the ideal of almost mathematics is the ideal cutting out spec W inside spec A. So all I'm going to do is I'm going to restrict to this slice and modify it by this map. So let's call this map alpha. And I'm not going to say anything about the construction of this map. But once you've constructed this map, you can sort of define A omega x as the homotopy limit of the fiber product of the following. So here you have A omega x, here you prime, here's A omega x prime tensor W. This is sort of the quotient in the special fiber, and then here's the de Rham-Witt complex. And I'm out of time, so I guess step 3 is that you check that this works. Oh, what?
You have 5 minutes.
I have 5 minutes.
Is it an almost isom, this map?
Which map?
The natural map, some map is almost isomorphic?
This one? I'm not sure. It's related to what we were discussing earlier. So I guess, no, I don't know. I would like it to be, and that would simplify some of the constructions. But I don't know if it's an almost isomorphism. Is that right? Wait, sorry, which one? This one? No. Alpha, it doesn't make sense to talk about almost isomorphisms because it's taking place over W.
Okay.
Yeah. Sorry, there's a version of this over W of OC where it does make sense. And I got confused. Yeah, no, so maybe I should. So we're really doing almost mathematics with respect to this closed immersion, whose ideal, as I said earlier, is cut out by P underline and all of its P power roots, and then you also have to worry about P-Adic completions. And then what I'm saying is that if you want to specify something over here, you first specify something in the almost world, which is A omega x prime, and then specify what happens when you restrict to the special fiber. And the way you specify what happens when you restrict to the special fiber is that you're allowed to arbitrarily modify it in this way. Okay. And then I guess I can write step 3 over here, which is kind of stupid, but it's where all the hard work happens. So check all the specializations. And so maybe I'll just say which ones use what. So to use that the étale specialization is correct, you use Scholz's theorem, which is some version of Faltings' theorem, comparing OX plus cohomology with étale cohomology. And then the other two you check by hand. So crystalline is more or less by construction. So the crystalline specialization is what happens when you restrict to W. And the way I'm modifying it, I'm forcing it to look like the de Rham-Witt complex. So this is by construction. And then the de Rham one you'd really have to check. Sorry?
To know it is a perfect complex.
So it follows from the fact that the specialization along the kernel of C gives you the de Rham complex, which is a perfect complex. And so I guess I should have said this, but you also have to C-adically complete everywhere. So everything is complete along the kernel of theta, and then when you specialize along theta, you get a perfect complex. And so it's a perfect complex. Okay, so that's all I wanted to say. Thank you.
Did you write the comparison theorem between the Galen and crystalline homology from this view picture?
Sorry, can you
derive the comparison theorems from the crystalline and the type homology from your picture?
I believe it's hidden in this picture, but in the same way that it's sort of, I don't think the proof you get would be any different from the one that you get by Faltings' machinery.
So I have two questions. First one, in classical story in Bertolo Roger's, the generation on the special of Hodge to the RAM E1 and the special fiber played some important role together with torsion freeness of crystalline cohomology to get a nice Hodge filtration. And it doesn't appear in your in this sort of new version. And,
Well, I mean,
you discussed torsion freeness in the RAM, but didn't discuss the generation. So is it important or is it?
You're talking about not the comparison theorem between.
So there's a notion of Meter-Roger's object, you see.
You're talking Mazur's theorem. You're really Mazur's theorem.
Yeah, but then you get that for example, the Hodge number of the special fiber of the same as abstract Hodge number of the filtration. So that under these conditions, degeneration that you want, Hodge to the Hodge special fiber plus torsion freeness. So I wonder whether there is some analog of this sort of.
I don't know the story, so I can't really comment on it. The only thing I want to say is that if the
Chapter 8 you mentioned, yes?
I'm getting old. The only thing I wanted to mention is that if the crystalline cohomology is torsion free, then each cohomology group is in fact finite free. So you really have a lot of things you can do with it.
So anyway, my second question was an obvious question, maybe related to the previous one. So is there any relation between this A omega dot X and the complexes constructed by Sasha, the curly A natural, and curly A natural Durham, curly A natural Crace, will give the P-Adic comparison theory?
I don't think so. I think the complexes constructed in the H localization picture are what you'd get if you did not do this modification at the end. Like if you do R gamma of A script A Durham, sharp.
Then you had this Sasha's Poincaré lemma, yes. So then here there's no such thing.
Well, I mean, somehow the comparison theorem is hidden.
It seems that formally it looks similar, so there should be some relation between two objects, no? Don't you think so?
So I guess maybe one thing I can say which is related, but not an answer to your question, is that you can ask if there's a way to construct this cohomology theory using the H localization picture. Yes. And I currently do not know the answer to this, although I suspect the answer is yes if you use topological Hodge homology. But no, this construction won't work because it's a local construction.
Okay, so yeah. Why do you get an almost isomorphism between A omega x and A omega dash x? You said that.
Oh, it's just because the way I'm modifying it by something that's almost zero.
You force.
So this side is almost zero, so when you pass back to the almost world, you just get an isomorphism. Like any module over W is declared to be almost zero.
Okay. Yeah.
So do you have chart classes?
Probably. I don't know, but I mean, I would strongly suspect yes.
Okay, so I have two questions. Maybe I will ask only one, and then I will do the other one later on. So yes, can you recover the integral comparison theorem that we had, for instance, with Bill? You see when so you look at the HI with I is less than P-1, and the modified situation. There should be a way to see.
So what you do get is that, so this map, this Frobenius map, specializes to the comparison isomorphism. And it's invertible up to this element C. So if your numbers, if the dimension is small enough, then you get some mileage out of it. Yeah. Like, so for example, Faltings has these theorems that say that integrally the comparison maps he constructs are always invertible up to beta to the D. And that's this fact that this map is invertible up to C to the D.
Up to C to the...
D, where D is the dimension of X.
And on particular cohomology groups, can you get C to the I or something like this?
That should be a formal question about this gauge construction, and I can't think right now, but I would guess yes.
Okay, so maybe if there are more questions, we'll talk later on, because let's thank the speaker again.